All right, so today we're going to start talking about section 6.1, which is the set of rational numbers. And as we start this, the first piece of information I want to talk about is what these things are. So rational numbers are numbers of the form a over b, and the word ratio. A and b have to be integers, or be able to be changed into something that would be an integer for it to actually be in rational form. So you can't have, for instance, 0.7 over 0.8. You'd actually have to multiply them both by saying giving an integer form for it to actually be expressed in rational form. And one caveat to this, one issue is what's wrong with the A and the B? There's a potential problem in the way that it's written. Any ideas? There's something B can't be. B can't be 0. So you could actually have a 0 on the top. A can be 0, but B can't be 0. All right, a fraction is a looser description than rational number, because a fraction can actually be any number a over b. So you could actually have in fraction form the a and the b be things that are not integers. They could be square roots, they could be pi, they could be fractions themselves, or they could be, they could be whole numbers or integers. That's fine. They have more flexibility for using them as they call a fraction. All right, the numerator. What's the numerator in these descriptions? The top, which is a, and the denominator is the bottom, which is b. Excellent. All right, so your book pulls up basically 4 overall uses for rational numbers. The first use of rational numbers is solving equations like 2x equals 1. If we were restricted to whole numbers, we would not have a solution for that. Whole numbers, remember, are positive and negatives, and they're the counting numbers, the ones that children count with. So for instance, if x is 0, 2 times 0 is 0, it's not 1. But if x is 1, 2 times 1 is 2, which is not 1, and we skipped over the number 1, which we were trying to solve for. So we have no way of solving that equation if we don't have the use of fractions or rational numbers. The next 3 are a little bit different, and you've seen them used somewhat, although partition may not be something you've thought of described this way before. So let me give you some examples of each of these. So a partition example would be something like this. 1/4 of my hay goes toward my gas. It's a portion of something. That's all partition means. So in this case, I've created something where it's a portion of the money that I make, and it goes towards a certain object that I make. A ratio would look something like that. This. Student to teacher ratio is 20 to 1, and that can also be expressed as 20 over 1. I know it looks sort of funny to have something written over 1, but as a ratio, that probably would be it. That's a ratio of this class. There's 20 of you to 1 of me. Most days. Probability. So probably a classic case example of probability would be something like this. When you roll a die, the probability of rolling a 2 is 1/6. There's 1, 2, and one side of the die has 2 dots on it, and there are 6 sides to the die, standard die. Probability is one of those cases of rational numbering usage. Let's do an example. This says for each of the following, write a fraction to represent the shaded portion. So I'm going to draw some images for you. One of the things that I am going to attempt to do, at least when I can, is actually do some of the drawing that you might in fact want to do if you were doing a presentation on a smartboard. And I do not pretend to know everything about the smartboard. Some of you in my class last semester did things on a smartboard that I don't know how to do, and that's pretty cool. So let me show you some of the things I do know how to do. So let's do A first. So the first thing I'm going to do is I'm going to draw a rectangle. So there's features at the bottom that have different shapes on them. This one's actually a square. The rectangle one's this one. So I'm going to draw a rectangle. And I want to take my rectangle and I want to divide it into some pieces. So I'm going to divide it using a line segment. I'm going to divide it in half lengthwise, mostly. And then I'm going to divide the top, just the top, into 3 pieces. And it isn't perfect, but you get the idea, right? There are other ways to create an image like this, but this is one of them. And I'm going to shade in this box right here. Okay, so this is the problem. This is not creation, is what I want you to see so much as. This is the question you would answer from your homework, right? It would look like this. It would say, using this picture, what is the fraction that represents the shaded portion? How much of this picture is shaded in? It is 1/6. Why isn't it 1/4? Because you're going to have some student in your class that's going to say, but Ms. Darvasek, it's 1/4. There's 4 pieces and there's only one of them shaded in. Why is it not 1/4? Right, so when we're working with students and we want to explain that, it might even be helpful to go ahead and draw the picture out. It is completed so that it looks like it is what we're actually experiencing. So something like this. So now I have the 6 equal pieces and I can talk about it from that perspective. Okay. All right, let's do another one, very similar. We're going to do a rectangle. Then I'm going to cut in half, lengthwise. And pretend like those are equal halves because they are not very equal, but pretend. We're going to draw these pieces in here. And I have this picture. How much of my diagram is shaded in? That one's 1/4. Now, that's really similar to the last one, except that the pieces look more equal than the last one did anyway, right? And I can't just take a piece and flat out divide it. I'd actually have to restructure how it was divided to make sense of that to a child, right? I would have to do something where I said, okay, but let's show the pieces that are equal to one another, maybe in a different color, and say there are 4 pieces that are all the same size, and one of those 4 pieces that are the same size is shaded in by 1/4. All right, let's try another one. We're going to do a circle this time. Okay, one thing about the smartboard is that it doesn't look very circular to you. It looks kind of like an oval. You just have to forgive the smartboard because the projection distorts it a little bit. It's actually very circular on my computer if you were to look at it. We're going to cut this in half lengthwise. And then I'm going to draw a few more divisions in here. Actually, it's not too bad. All right, so we have this image shaded like this. All right, how much of this image is shaded? Okay, so 1/3 is one way to answer it. How else could you answer this? And so this one leads itself to giving a really good description of how to reduce fractions without the typical, oh, the number 3 goes into the top and it goes into the bottom, sort of a numerical approach. You can do this from a picture approach, right? So you can count the boxes up. There's 2 shaded, there's 4 that aren't, 6 boxes filled, so it's 2 out of 6. But you can talk about why that would reduce to 1/3 by making 3 equal pieces. There's one of them. It's equal to this one and that one. So there's 1 out of 3 larger size pieces shaded in. Pictures are great to talk about reducing fractions. I have one more for you. All right. Here's a cool feature of Smartboard 2. I'm going to draw one small circle, but I want a whole bunch of circles that look just like that one. Okay? So I'm going to take my tool and I'm going to click on it. I'm going to use this arrow, it drops down. I can copy and paste, that's one way to do this. I can also do clone, which automatically does the copy and paste. What I want to do is I want to do infinite cloner. which will let me do the following. I can drag identical images off the top of the one that I've infinitely climbed. What do I have? Okay, so that's what we've got. And you can also take these images and you can shade them in. So I'm going to take this one and, all right, where's my thing? We're going to shade them in a color, and you can pick whatever colors you want. And you may, if you were doing this in a classroom, do some of this stuff beforehand. But I want you to see what I'm doing, not just see what cool stuff you can create beforehand without me being there. So we're going to color in a few of these dots. And these dots that aren't even just blue, right? They're actually a gradient fill, which is kind of pretty. All right, so how many of my dots are shaded in? 7 out of how many total dots? 12. And this would actually, if I had done something like a 6 out of 12 or a 4 out of 12, it would also be something where you put it in groups and bunch them together, right? And actually talk about reducing it where it makes sense. All right, so a couple of notes now, historical notes, if you will. We aren't sort of the first people to use fractions. Surprise, but use of fractions is actually quite old. Egyptians used fractions, but they used fractions that only had numerators of 1. And so instead of writing a number, for instance, like 7 over 12, like the last example we just did, they wouldn't write it as 7 over 12. They would write it down as a sum of things that had numerators of 1. Who's glad we don't do that anymore? I am, because I think that sounds more complicated than what we do. So they would write it as 1/4 plus 1/3. The Greeks adopted fractions with denominators of 60 from Babylonians, still presently used in the measurement of angles. So has anybody taken a trig class before and you talk about angle measures and you do things with 60 degrees? The Babylonians did things with 60 degrees. If you've taken contemporary math or if you've taken elementary math 1, we talk a little bit about the Babylonians, and they have a base 60 number system. That should ring some bells for many of you. That's what's coming from this. Okay. Not only that, but the base or the 60 for the trigonometry has to do with angles related to degrees, minutes, and seconds. You can think about our clock even, right? So we've got our seconds and our minutes in the 60 system, right? We talk about 56, right? 156 goes up to 60 before we start counting over and whatnot. And then the Hindu are the ones who developed the modern bar between our numerator and denominator, that horizontal bar that we use. That actually came about in the 1500s. Now, there are several models for rational numbers. And lest you think that this is not very important for whatever grade you deem yourself to be teaching in the future, let me assure you that fractions are taught in 3rd grade. You know that? 3rd grade. My daughter's been bringing home information about adding and subtracting fractions. 3rd grade. So things are not taught in exactly what you remember them being taught when you were in elementary school. So many of you thought you were avoiding fractions by teaching 3rd or 4th grade. Surely fractions aren't taught that young. Well, they are now. Maybe not all of the complexity of it, of course, but there are aspects of fractions that are being taught at the younger levels. All right, so these are some different models for fractions. The area model is the first one we're going to talk about. And we'll use the tools again. All right, so an area model is drawn much like a box. And we're going to draw an area model for a portion. It's going to be, or the example we're going to do is 3/4. So, I mean, you could use an area model, you could use a circle. It didn't have to be a rectangle, because rectangles are typically a little easier to work with, especially the more complicated your fraction is. So 3/4 works pretty nice. We're going to take a box and we're going to divide it into how many pieces? 4, and we can do that pretty well because we can half it twice, right? And then how many are we going to shade in? 3. All right, so that is a representation, an area representation of the number 3/4. Okay, we're going to do the same example, 3/4, for a number line model. So a number line model takes a line segment, or a line, either way, and it starts at 1 point, 0, and it ends, partitioned out, at the number 1. The fractions we're working with are proper fractions. They're going to have a numerator smaller than the denominator for the moment. This model is anyway. So we can go from 0 to 1. And 3/4, well, we would do kind of like what we did with this picture up here. We'd half it, right? And then we'd half it again. So this ends up being 1/4, 2/4, or you can label it 1/2, of course, and 3/4. If it had been drawn well, that 3/4 would be more centered. It's not. And this would be the number line example of 3/4. And to show that we actually mean this full length, not just the location, we will actually draw it like this. So this is actually 3/4 in a number line model. The set model you've already seen used. I used it when I was doing my infinite cloner just a little while ago. So the infinite cloner with the set model, again, 3/4, has us draw however many the denominator is, circles. So we're going to draw one circle. We're going to clone it so that we can get 3 more just like it. And then we want to shade in how many of them? 3. Because it says 3 out of 4 of them are shaded. Now, there's a note in bright red on my screen that says the set model has limitations. Let me show you what I mean by that. Let's say, for instance, that you had 5 cookies. And your 5 cookies look an awful lot like, okay, just a second. All right, I've got 5 cookies, and I've got several children that want my 5 cookies, and it's not 5 children. Well, what do I do with the 5 cookies if I want to shade, if I want to give each child 3/4 of the numbers of cookies I have? It's sort of problematic. I mean, like, I can give you 3/4 of my 5 cookies, but if I have 5 cookies, that's awkward visually. Are you following what I'm saying? I mean, it's great if I only had 4 cookies. I could just eat one of the cookies, and then the 4 kids could each have a cookie. That's probably what I would do, right? But that doesn't really answer the math question that we're sort of looking at, yeah? So, yeah, I mean, this is sort of has limitations. We really need to be able to sort of draw this picture based on the fraction, not create a fraction based on the number of items in the picture. So we run into problems. All right. So let's get some mathematical computation skills in here now. We've got a fraction a over b. We talked about that. We're going to let n be a non-zero integer. Okay, so it can be 5, it can be -2, it's anything. Sorry, I said non-negative. No, non-zero. I was trying to switch to non-negative. So we can even have it negative, we can have positive, whatever. It's just a number. And it is equal to the original fraction, a over b, as long as we multiply that numerator and the denominator by the same number. You guys know this, right? Not only is it true with multiplication, but it's true if we start over here and we move back to the other side, right? We can actually take a number, like we did just a moment ago, where we had 2 over 6, and we can divide both the top and the bottom by some number and move back to a simplified form of a fraction. So this ability to move back and forth by multiplying or dividing by a value is theorem 6.1. And that actually allows us to do what's called simplest form for a fraction. So a rational number is in simplest form if, first, the denominator is considered positive. So if the denominator is not positive, can you change it? Sure, you just move the negative somewhere else. You can move it up. So it's a minor kind of detail, but it is part of it. And then the greatest common divisor, that's what GCD means. Okay. The greatest common divisor of the top and the bottom is 1. In other words, They don't have any numbers that they both divide by, besides one. They always do both divide by one. They don't have any other common factors. All right, so let's do an example. We're going to write three fractions that are equal to 3 over negative 14. All right, so I need a volunteer. Oh, big volunteers. All right, Megan, come up to the board. The class can help you. You're just going to write, okay? So you don't have to do it all by yourself. Somebody tell Megan a fraction that she can write that is equivalent to 3 over negative 14.
6 over negative 12.
All right. Can you write that one for us, Megan? Excellent. Someone else tell her another one. Thank you. Negative 3 over 14. In your mind, you might not have thought that was any different, but it is, right? It's a different number. It means a different expression. We need one more.
Negative 6 over 28.
All right, Megan. That'll work. And we could do this literally speaking all day. We can come up with plenty of others, right? There's nothing special about these three. We can come up with whatever we like. Now, example 2 is a simplest form problem that I wanted to draw your attention to because I don't want you to think that you have some sort of property that you don't. Here's what I mean. On this particular problem, you have the numerator squared and you have the denominator squared, right? And I would love it just as much as you would if I could just sort of like cancel out the squares. And that is totally not option, okay? We do not have that option at all. We have lots of things we can do, and one of the things we can do is we can look for common factors, ignoring the squared for a moment. Okay, so just looking at the numbers 42 and 35. What number do each of those have in common? They both have a 7. So I'm going to write 42 as 7 times what? 7 times 6. And the denominator as 7 times 5. All right, now they both happen to be squared, so if you actually made the mistake of just drawing a line through the 7s and thinking you're done, you actually end up with the right thing on this particular one. But hold with me for a moment to consider what squared means. What does something mean for it to be squared? Multiply by itself. So literally what I have on top is I have 7 times 7 times 6 times 6. Or you could write 7 times 6 times 7 times 6, however you want to write it. I got 2 7s, I got 2 6s. That's a commutative property of letting you move them around. And what do I have on bottom? And now I can use theorem 6.1 in reverse. Right? So theorem 6.1 said that I could take a fraction and I could multiply it on top and bottom by the same number. But when we presented 6.1, I told you could do that in reverse, and you could also divide the top and the bottom by the same number. And that number in this particular problem would be 7. And we can do it twice, right? So these two divide out and these two divide out. What does that leave me with? 36 over 25. And unless you're told to do so in a problem, and I'll show you another case where it's here too, there's no reason to change this into a mixed number. It's fine, just leave it as 36 over 25. Alright? Alright, another theorem, another computational fact about fractions. So if you have a fraction a over b and another fraction c over d, and they're equal, right? So in other words, you have, let me write it down here. A over b equals to c over d. It says you can do what? Cross multiply is a word that some people use, right? So you can multiply these two together, and that gives you AD. You can multiply these two together, and that gives you CB or BC on the other side. And those two multiplications will be equal. So I had one of my students, and if they've been here, I can't even bring them out. Talk about that looking like a butterfly. Maybe a butterfly imagery. Example 2 says, determine if the following fractions are equal. And then it says, note in red, there are at least 4 ways to do this. One of them is what? cross multiply, right? Because it's on the same slide as cross multiply. So, yeah, one of them is to cross multiply. So option number 1, we could cross multiply. So I've got negative 3 over 12, and I want to show that it equals negative 36 over 144. Put where you want the negative to be. I'll put them on top. Not that it matters, but that's just where we stick them. You can put them on top. And we're going to cross multiply. So, what is, if you have a calculator, 3 times 144? Well, it's negative. And what? 432. And then, what is 12 times negative 36? And 432. And they match, which is kind of the point, right? Yeah. So we verify that they're equal. So the original fractions are equal. So I feel like I should tell you, since I told you there was 4 ways to do it, maybe like one of the other ways. Would that be good? Because you may not want to multiply those numbers together if they were large enough and you didn't have a calculator. It might not be what you would want to do or think to do or you would reasonable to do. So let's try another option. We're going to simplify and compare. All right, so we have negative 3 over 12, and I have negative 36. Well, you know what, let me come back to that one. Oh, goodness, what happened? Okay, negative 3 over 12. So negative 3 over 12 is not in simplest form. How could I simplify it? What? What's that? Negative 1/4. How did you do it, Kayla? Sorry. All right, so you divide top and bottom by 3. So this would be negative 1/4. And then we've got negative 36 over 144. It might take you a couple steps, because you might look at 36 and 144 and say, would they both divide by, they're both even, so you might try that first. Say that's what you did. You said, oh, they're both even. So what is negative 36 divided by 2? Negative 18. And 144 by 2? 72. Again, they're both even, so we can go again, right? Negative again, negative what? 9 over 36. At that point, you might look at that and say, oh, 36 is a multiple of 9. I can divide them both by 9. And you get negative 1/4. So you could simplify them both to compare. This would be an option. Especially if one of them was already simplified, that might be a nice option, right? You didn't have to do it twice. Let's do number 3. You could find the least common denominator. So if you compare 12 and 144, what is the least common denominator? 144. So here's 144, and you have the negative 36 already. And you could take your negative 3 and your 12, and what would we need to multiply the denominator by to get 144? 12. And what's 3 times negative 12? Negative 36 over 144, and obviously they both match now. So number 4 is interesting. I will guarantee without a doubt that I never heard anybody describe this when I was learning about fractions, but it is a very reasonable thing to do in some cases. This one says to find a common denominator. So sometimes when you're working with numbers, you could find the least common denominator, but it would be a lot easier to just find a common denominator and compare. That's what I'm trying to do anyway, compare them. Now, in this particular one, we've already done the least common denominator, so it sort of seems silly. But, hang with me for a minute and let me show you. So we have 12 and we have 144, correct? What would a common denominator of 12 and 144 be without worrying about it being at least 1? No? No? So at least 21.
So
No, because you can't take 144 and turn it into 12. Anytime you have a common denominator, it's bigger than the number you already have. Common denominator, at least common denominator has to be bigger than what you already got. I think that's clear. Think with this for me. What if you had 1/4 and 3/5?
it's like 20.
So you get 20 because you
Minus the denominator.
multiply the denominators together. Anytime you multiply the denominators together, you will get a common denominator. Now, in the one I just wrote up here, it would be the least common denominator as well, but what if I did 1/4 and 1/2? Granted, the least common denominator is 4, but 8 would be a common denominator as well. We could do that. It's kind of overkill, but sometimes it's easier to work with it that way. I'm not promising it's easier on this one, but somebody multiply for fun. 12 times 144 for me. 520? 28. Awesome. All right, so 528. So the first one was -3 over 12, and we multiplied the denominator by 144, and we got 528. So I also have to multiply the numerator by 144. So what's 3 times 144? 413. Negative, right? What did you say? 432. I'm sorry. All right, and then we're going to do the same thing to the fraction -36 over 144, except we're multiplying by 12. Denominator is still 528, and the numerator is -432. So you might be looking at this and saying, why in the world did you choose that? Oh, is it not 528?
It's 17.
What was it?
1,700.
1728. That's okay. We can fix it. A little bit of erasing, no problem. 1728?
Yeah.
Well, you know, I have answers on the paper, and I didn't look at it either, so. All right, so 1728. All right, so taking a look at this then, you might look at this and say, why in the world do we need to know how to do so many 4 ways? And the reason you need to learn how to do so many 4 ways is because you're not learning this material. What are you doing? Teaching it. And did you know that a lot of times you don't have a lot of control over what you teach? Nobody told you that, did you? Did they? Right, so sometimes the curriculum you have will go one direction and you need to be able to support that curriculum. But at the same time, you need to be able to help a child who can't figure out that curriculum and why that works to be able to do something different, right? So you need to be able to think about it from different perspectives so that you can help your students be able to think about it from different perspectives. All right, 6.3. A is your integers and B is positive. Then if you compare A over B and it's greater than C over D, that will be true if and only if A is greater than C. If B is negative, the reverse is true. So in other words, if the denominators already match, right, then we've got some sort of a relationship, whether it's being equal or greater than or less than between them. And we can talk about the relationship between the numerators only in very much the same way as talking about the fraction relationship, that is, the inequality goes in the same direction, as long as the denominator is positive, right? So this is a greater than sign, and this one's a greater than sign. And if the b is negative, the denominator is negative, then the direction of the inequality will change. And you guys encountered this at some point in algebra when somebody told you when you were working with inequalities. If you multiply or divide by a negative, you have to change the direction of the sign. That's where you sort of heard it said before. If you don't remember, it's okay. But this is what's going on, is it's talking about it from this perspective. All right, theorem 6.4 says that if you have these fractions, again, in this sort of a ratio, but now your denominator can be different. We've got a over b and c over d. That the fraction's going to be bigger on the left-hand side if I can cross-multiply it and the left-hand side value is bigger. So I cross-multiply just like I did when I had equality, okay? That's good. And the direction of that inequality symbol, the less than or greater than, which one we're going to had will remain the same. All right, so we're going to arrange these three numbers in order. There's several ways to do that. Do you have a volunteer? Volunteer. Kayla, come on up. You don't have to be the only one answering. You're just going to be one writing. That's all you're doing. Okay, so Kayla's going to write. What do you think we should do to figure out the order that would be correct?
Find the common denominator.
Common denominator is a really good way. Grant, do you know what the common denominator would be?
We could use 20.
You could use 20. That sounds good. So the first one's already done for you, right, Kayla? So just write 13 over 20 down. All right, so how am I going to change 3 over 5 so that it has a denominator of 20? Right. Multiply on 4 on top and bottom. So what does that one give us, Kayla? No, just write down what you got. Okay. All right, and then how about 7 over 10? What would we do? Top bottom by 2. Okay, so looking at them in order, say first fraction, second fraction, third fraction, which fraction is the smallest? Which one? The middle one, right? The 12 over 20? The 12 over 20 was what our, sort of our work to think about is. What was the original fraction? 3/5. So you're going to write in order, Kayla, so on the next, just kind of move over on this side of the board. You're going to write down that 3/5 is the smallest, right? So write down 3 over 5. And then put a less than sign because it's the smallest. What's our next fraction in order? 13/20, and that was actually our original fraction, so we're going to write 13 over 20. And then which one's next smallest? 7 over 10. So you see, your answer, your answer is in simplified form, but the work to get to the answer had to get, one of the ways to do it was to get it in a form that actually had common denominators. All right, looking at number 4. Less than, greater than, or equal to. What should go in that blank? And or how would you figure it out? You can't tell immediately. You could cross multiply. Okay, so that's one way to do it. Or you want to do it first? Just do it on the left-hand side, because I'm going to do another option too. Yeah, but you don't have to, but you can. Somebody help out Lauren with multiplying these, because the numbers are a little bit unusual. What is 21 times 215? 4,000. And what about the other one, the 430 times 51?
21,930.
What?
930.
So what symbol should go between those words? Right, the less than one. The first one's smaller, correct? Yes. So it's okay, put the less than symbol between it. And then that means the same symbol, the less than symbol would actually go between the fractions, right? What's another way besides? Good. You could estimate, because Haley, roughly, what do you see going on here? Yeah, this number is smaller with a bigger denominator. This number is bigger with a smaller denominator. So you should be able to sort of look at that and think about it from that perspective, right? And you can actually do it with estimations and rounding. You can help see that. Yeah. Another option? You get a common denominator, which would actually work pretty nicely with these because the common denominator would be 430. So you could just multiply the 51 and the 215 by 2 and it would work. So any of the ways you do it, though, you end up getting the correct symbol, which is a less than symbol. Yeah. All right. All right, let me make a comment about these two and then we'll pause for today. All right, so the next two properties talk about, or theorems talk about density. And so density is this idea that between every two numbers, there's another number, okay? So the density, and that's true for rational numbers. It doesn't work for integers, right? There's no integer between 1 and 2. This is definitely not a property of just numbers in general. It's a property of fractions, though. Given two different rational numbers, a over b and c over d, there is another number between them. Okay, think about a number line. That should make sense, right? If you fill in a number line, you got the two numbers, there's a number, lots of numbers, but at least a number halfway between. Agree? All right, so theorem 6.6 tells you one way to find one such number. So if you have a over b and it's smaller than c over d, one way to find a number between them is add the two numerators together and divide that by the two denominators added together. So that's kind of cool. Now, some fractions, this is unnecessary for. If I asked you for a fraction between 6/8 and 8/8, you would say 7/8, right? Because there's space sort of work between them. But if I asked you for a fraction between 3/5 and 4/5, right? There's no space there to work with. You might be able to say 4.5 and change the fraction around. That's perfectly fine. But you might also do this. This is another way of handling that. So you can add the two fractions together, numerator and denominator independently, and that will be between your numbers. So when we come back next time, we're going to do that for this fraction. Have a wonderful day, and I'll see you all on Thursday.